Welcome to the deep dive. Today, we're tackling something, well, pretty foundational: data structures.
Yeah, absolutely fundamental.
These are sort of the hidden frameworks, right? The way computers organize, manage all that information they deal with.
Exactly. Everything.
Now, I know it might sound maybe a bit dry, like Computer Science 101,
It can sound that way.
but really digging into how these structures work gives you, I think, a much deeper appreciation for how technology actually functions, and maybe even helps with problem solving generally.
I completely agree. It's like understanding the grammar behind the language.
Oh, I like that analogy.
Yeah, once you know the grammar, you can build complex sentences.
Yeah.
Once computers understand data structures,
Yeah.
they can handle huge amounts of information efficiently.
Okay.
So our mission for this deep dive really is to give you a solid, clear picture of how these structures are classified. We'll focus on two main things: the logical links between data bits, and then how that data is actually physically laid out in memory.
Logical and physical. Got it.
And getting this foundation right is, well, it's key for understanding pretty much everything else that's more complex in computer science. Try to make it approachable.
Good. So where do we start? Logical structures?
Let's start there. Logical structure is all about the concept, the idea of how data elements relate to each other. It's abstract, separate from where they're physically stored.
Okay, so like how I think about organizing my music library versus where the files actually are on the hard drive.
Perfect example. You might think of it by artist or album or genre. That's the logical structure you impose. The MP3 files themselves might be scattered all over the disk, but your music player presents them based on that logical relationship: artist, album, whatever.
Right, the logical view versus the physical reality.
Precisely. And these logical structures, they mainly fall into two big camps: linear and nonlinear.
Linear sounds like one. It's straightforward.
Exactly. Linear data structures are the ones where elements follow each other in a sequence, one after another, like beads on a string. Think of a simple numbered list or the steps in a recipe. Each item has a before and an after, generally speaking.
Makes sense. What are some examples?
Well, the sources mention things like arrays, probably the most basic ordered list, and you have linked lists, which are also sequential, but a bit more flexible.
Okay.
Stacks.
Yeah.
Think of a stack of pancakes. Last one on is the first one off.
Last in, first out. LAFO.
Right. And queues, like waiting in line, first person in is the first person served, first in, first out, or FIFO.
FIFO, yeah.
And interestingly, hash tables get mentioned here too.
Yeah.
We'll definitely need to circle back on why they pop up in different categories.
Yeah, that sounds intriguing. But the core idea for linear is sequence, one after the other. Feels intuitive, like you said. A to-do list fits that perfectly.
It does. You work through it, maybe reorder it, but there's a sequence.
So what about the other camp, nonlinear? Sounds messier.
It can be, or maybe just more complexly connected. In nonlinear structures, data elements don't just follow a single path. An element can be related to multiple other elements in various ways.
Okay, so not just a simple next.
Exactly. Think of a mind map, maybe.
Yeah.
Or a family tree. One person can have multiple children who have multiple children. It branches out.
Yeah.
Examples from our sources include trees, which are these hierarchical structures, heaps, which are a special kind of tree, graphs, which represent networks. And again, hash tables make an appearance.
Hash tables are everywhere.
Huh?
Okay, so trees, graphs. Can we break those down a bit?
Yeah, the sources do. Tree structures generally have a one-to-many relationship, like that family tree ancestor-descendant idea. One parent node can have several child nodes. Trees, heaps, and apparently hash tables can fit this mold sometimes.
One to many. Like a company org chart.
Yeah.
One manager, multiple reports.
That's a classic tree structure. Then you have network structures, which are defined by many-to-many relationships.
Many to many.
Yeah, think about your social network connections. You're connected to many people, and they're connected to many other people, including some you're connected to. It's a web. Graphs are the prime example here.
Okay, yeah. My LinkedIn connections are definitely not a neat tree. It's a total graph. That analogy helps a lot.
Good. So that's the logical side, how we conceptualize the relationships. Linear sequence versus nonlinear branching or networks.
But you mentioned hash tables in both. Still hanging there.
We'll get there, I promise. It ties into the next piece.
Okay. The physical structure, how this stuff actually gets stored.
Exactly. Physical structure is all about the arrangement in the computer's actual memory.
The hardware level.
Right. Our sources use a nice analogy. Picture computer memory like a giant spreadsheet, maybe, a massive grid.
Okay, rows and columns.
Kind of, but think of each cell having a unique address, like cell A1, A2, B1, B2, but, millions or billions of them, each with a specific numerical address.
So every tiny piece of data gets its own address in this giant grid?
Precisely. A number, a letter, part of an image, it all lives at a specific memory address. And programs find the data they need by using these addresses. Now, memory isn't infinite, right? It's a shared resource. So how we physically place data in this grid matters a lot for performance.
Like how fast you can get it back.
Exactly. And also how efficiently you use the space. Do you need all the pieces of your data sitting right next to each other, or can they be scattered around?
Okay. So there are constraints. You might not find a big enough empty block altogether.
And that's a key consideration. This leads to the two main ways physical storage is handled: contiguous space storage and dispersed space storage.
Contiguous sounds like together.
Exactly. Contiguous storage means putting data elements in memory locations that are right next to each other, physically adjacent, like a row of reserved seats in a theater.
And the main example is?
Arrays. The classic array. When you declare an array of, say, 10 integers, the system tries to find 10 adjacent memory spots and reserves that block.
Okay. All in a neat row. What's the benefit?
Speed of access, mainly. If the computer knows where the array starts, the address of the first element, and how big each element is, it can instantly calculate the address of any element in the array. Like getting to the fifth element is just start address plus 4 element size, super fast.
Direct calculation. No searching needed.
Right. But the downside is you need that unbroken block of memory, which might be hard to find if memory is fragmented, and arrays are usually fixed in size once created.
Okay. So what's the alternative? Dispersed storage.
Dispersed space storage. Here, the data elements don't have to be neighbors in memory. They can be scattered all over the place.
But how does the computer know which element comes next if they're not lined up?
Good question. It uses pointers or links. Each data element stores not only its own data, but also the memory address of the next element in the sequence.
Like a treasure hunt. Each clue tells you where the next one is.
Exactly like that. The prime example here is the linked list. Each item points to the next item, forming a chain, even if the items themselves are in totally different parts of memory.
Okay, so you follow the pointer.
You follow the pointers. The big advantage is flexibility. You don't need a large continuous block of memory. You can grab free spots wherever they are. This makes it easy to grow or shrink the list.
But I guess finding, say, the 100th item takes longer. You can't just calculate its address.
Correct. You generally have to start at the beginning and follow 99 pointers to get to the 100th item. That's the trade-off. Flexibility versus direct access speed.
Contiguous arrays are fast for access but rigid. Dispersed linked lists are flexible but slower for random access.
You got it. Those are the two fundamental physical storage strategies.
Okay, so we have the logical ideas, linear, nonlinear, and the physical storage methods. Contiguous arrays, dispersed linked lists. How do they connect? Does a linear logical structure always use an array?
Oh, yeah. That's the crucial connection. And the answer is no, not necessarily. This is a key point our sources highlight. Almost all data structures, no matter how complex they seem logically, are ultimately built using arrays, linked lists, or sometimes a combination of both.
Really? So arrays and linked lists are like the Lego bricks for everything else?
That's a great way to put it. They are the physical building blocks.
Okay, give me an example, like a stack. Logically, it's linear, last in, first out.
Right. You can build a stack physically using an array. You just need the array itself and a variable to keep track of the index of the top element. Adding means putting an item at the next index and incrementing the top tracker. Removing means decrementing the tracker.
Makes sense. Simple.
But you could also build a stack using a linked list. The top of the stack would just be the head of the list. Adding means creating a new node and making it the new head, pointing to the old head. Removing means just making the second element the new head.
So the same logical behavior LIFO achieved in two different physical ways.
Exactly. Yeah. And the same applies to queues, FIFO. You can implement them with arrays, maybe using a circular buffer technique to be efficient, or with linked lists, adding at the tail, removing from the head. The choice depends on the specific needs. Do you need fixed size and fast access array, or variable size and easier insertions, deletions, linked list?
This really clarifies things. The logical concept is separate from the physical implementation choice.
It is. And now, let's revisit the hash table.
Yes. The one that appeared as both linear and nonlinear. How does this physical implementation stuff explain that?
Okay, so here's the aha moment, hopefully. Hash tables often use both arrays and linked lists physically.
Both. How?
Typically, a hash table starts with an underlying array, Let's call it the bucket array. When you want to store something, you calculate a hash, basically a number based on the data, which tells you which index or bucket in the array to use.
Okay, so the hash points you to an array slot. Seems linear enough so far.
Right. But what if two different pieces of data happen to hash to the same array index? That's called a collision.
Yeah, what happens then? You can't put two things in the same array slot.
Exactly. So a common solution is, instead of storing the item directly in the array slot, you store the beginning of a linked list in that slot.
Ah, so each array slot can potentially point to a chain of items.
Precisely. If you hash to an empty slot, you put your item there or start a list with one item. If you hash to a slot that already has items, you just add your new item to the linked list hanging off that slot.
I see. So the array gives you the initial placement, but the linked lists handle the collisions by creating these little sequences within each bucket.
You got it. And that's why it has both characteristics. Within each bucket's linked list, the elements are sequential linear. But the overall structure, with multiple starting points in the array potentially leading to these chains, isn't strictly linear. It has branching aspects, sort of like a nonlinear structure.
Wow, okay, that makes sense now. The physical implementation, using both contiguous arrays and dispersed linked lists, directly creates that hybrid logical behavior.
Exactly.
Yeah.
And this also ties into the idea of static versus dynamic data structures.
Static and dynamic.
Generally, implementations that rely primarily on arrays are often called static because the array size is usually fixed when you create it. You decide up front, I need space for 100 items.
Okay, fixed size.
Implementations based on linked lists are often called dynamic because they can easily grow or shrink while the program is running. You just add or move nodes using those pointers, grabbing memory as needed.
So more flexible size-wise.
Right. It's that trade-off again. Static array-based structures might offer faster access sometimes, but dynamic linked list-based structures offer flexibility in size. Hash tables, using both, get a bit of both worlds, though managing the array size efficiently is its own challenge.
It's all about trade-offs, isn't it? Speed, memory use, flexibility.
Always. There's rarely one best data structure. It's about the best one for the specific job you need to do.
Okay, let's try and sum this up. We've got these two ways to classify data structures. First, logically, how we think about the relationships. Is it linear, like a list, or nonlinear, like a tree or a graph?
Right. Conceptual relationship.
And second, physically, how it's actually stored in the computer's memory. Is it contiguous, all packed together like in an array, or dispersed, scattered, but connected by links or pointers, like a linked list?
Exactly. Storage reality.
And the really key thing is that the physical building blocks arrays and linked lists are used to construct almost all the logical structures we think about.
That's the core takeaway. Stacks, queues, trees, even complex graphs are ultimately implemented using combinations of these fundamental contiguous and dispersed storage techniques.
And understanding that relationship, like how the hash table uses both, helps explain its properties and why you'd choose one implementation over another.
Absolutely. Knowing this classification, logical versus physical, linear versus nonlinear, contiguous versus dispersed, gives you a really powerful lens. When you encounter some new data structure later, you can ask, okay, what's its logical shape? And how is it likely built underneath with arrays or lists? That tells you a lot about its strengths and weaknesses.
It stops being just a name and starts being something you understand structurally.
Precisely. You understand why it works the way it does.
It really does make you look at everyday organization differently, too. My email inbox sorted by date, that's linear. The folders on my computer, that's a tree, nonlinear. My actual friends group, definitely a graph.
Ah, yes. These concepts are everywhere once you start looking. They're fundamental ways of structuring information, whether it's digital bits or, just stuff in our lives.
So, maybe a final thought for everyone listening. Next time you're organizing something, anything really, maybe take a second. Is the information best thought of as a sequence, a hierarchy, or a network? Thinking about that underlying structure, that logical versus physical idea, might actually give you some insights into the best way to manage it.
That's a great thought. Just like choosing the right data structure is critical for efficient software, understanding these principles might help us be more efficient in how we structure and handle information everywhere. It's a fundamental skill.